Okay, we're going to begin with some basics, naming and identifying organic molecules, and then we're going to look at physical properties and isomers. So, firstly, ignore the mix and match instructions. That's for someone who's actually got a class with them. Here are the prefixes. You should know these all by heart. The first 10, meth, et, prop, and so on, especially the first 8, but also good to know numbers 9 and 10. Okay, naming side groups. So we named by the suffix "-il", so methyl, ethyl, propyl, butyl, and so on. If there are more than one side chain, we can label them as di or tri or tetra. So for example, dimethyl means 2 methyl side chains, tributyl, 3 butyl side chains, and so on. Yep, so there are the first 4. That's probably all you need to know. Okay, the naming of our all of our organic molecules. We've got alkanes, alkenes, alcohols, haloalkanes. So like chloromethane or chloroethane or bromopentane or whatever. Amine, so methamine, ethamine, propamine, and so on. Carboxylic acids, methanoic acid, ethanoic acid, and so on. Aldehydes, so with the prefix anal, so methanal, propanal, pentanal. Ketones, the prefix unknown, methanone, ethanone, and so on. Sorry, you can't have methanone or ethanone. Propanone, butanone, pentanone, and so on. Esters have 2 parts, so let's say we had like methyl pentanoate or ethyl butanoate. Those are 2 examples. Acyl chlorides, methyl chloride, ethyl chloride, and amides with the suffix anamide, methanamide, ethanamide, and so on. Okay, now let's look at physical properties and isomers. Firstly, almost all organic molecules involve quite weak intermolecular forces, some stronger than others, but generally the intermolecular forces are weak. In some molecules, they have things like hydrogen bonding, so they have stronger. But compared to other types of bonding like ionic or metallic, the intermolecular forces are relatively weak. As the carbon chain gets longer, the melting and boiling point increases, which is due to increased van der Waals forces between each molecule, or instantaneous or temporary dipole forces. Solubility: as the carbon chain gets longer, the solubility decreases. And that's due to the polarity of the molecule decreasing as the carbon chain gets longer. Isomers, important. Okay, there are 3 types: constitutional or structural, geometric, and optical. Constitutional or structural is the most basic, where the compounds have the same atoms, the same molecular formula, but a different arrangement of those. Geometric are where you have a double bond. So you have restricted rotation around a double bond. You must have 2 different atoms or groups on each carbon atom. So the carbon atoms either side of the double bond, both of those atoms must each have 2 different things attached to them. They can't have 2 of the same thing, or they won't form geometric isomers. Cis is where the same groups are on the same side of the double bond, and trans is where it's like diagonal. The same groups are on different sides of the double bond. So for example, this is cis-butene, and this is trans-butene. Okay, it's diagonal, like sisters, same side. Okay, this molecule does not have geometric isomerism because this carbon here has 2 of the same thing attached to it. Okay, each carbon atom must have 2 different things attached to it. Alright, let's skip through that. Optical isomers, where we have a mirror image. They are a mirror image of each other. Think of it like your left hand and your right hand. They look almost the same, but you can't take one of your hands and rotate it to get the other hand. You can only get one hand by flipping the other hand in its mirror image, reflecting it. So we must have an asymmetric carbon atom, which has 4 different groups of atoms attached to it. That's the requirement for optical isomers to form. Yes, this is what I was talking about, the hands. You can get from one hand to the other by reflecting in a mirror, but you can't get from one hand to the other by superimposing. Even if you rotate it, you still don't get from one hand to the other. Yep, so fluoromethane is an example of a molecule that is not optically active, that does not form optical isomers. These are the same molecule. You could rotate what you've got on the left to get what you've got on the right. This molecule here, however, is optically active. You could not take the molecule on the left and rotate it to get the molecule on the right. They are different molecules. They'll have the same physical properties, but the way they interact with plane polarized light is different, and we'll see what that means soon. Okay, so we call these molecules chiral or optically active. Okay, here's an example. Is this molecule optically active? The answer is no, because the carbon has two of the same thing attached to it, CH3 and CH3, not optically active. How about this one? This one is optically active because this carbon atom has 1, 2, 3, 4 different things attached to it. This one is not optically active. There are no carbons with 4 different things attached to them. Yes, that should give you an example. We call the two forms of the optically active molecule, we call them optical isomers or enantiomers, and we distinguish them by plus minus DLRS. It's always used to distinguish the two enantiomers from each other. If we have a 50-50 mixture of enantiomers, we call it a racemic mixture or racemate. Okay, here's just some more examples of molecules that are or are not optically active. What you might like to do, I'm gonna skip through it. I'm not going to spend time on this, but if you want, just pause it on each one and see if you can work it out for yourself before I give you the answer. 3-methylhexane is optically active. Butanone is not optically active. 2-methylbutanoic acid is optically active. Butanol is also optically active. 1-chloro-3-methylpentane is optically active. Okay. Now, I said earlier that enantiomers or optical isomers have identical chemical and physical properties, except their effect on plane polarized light significantly, and also their reaction with other chiral molecules. Light is a form of electromagnetic radiation, so visible light is this narrow band in here of wavelength of light, but it's just a type of, we've got infrared light here. It's a type of electromagnetic radiation. So what we find is that normal light from the sun or from a light bulb vibrates in all directions. Plane polarized light, on the other hand, only vibrates in one direction. And then we can observe the rotation of that as if we pass that light through an optically active substance. So what we find is that optical isomers rotate the plane of plane polarized light in one of two directions. The plus enantiomer will rotate in the clockwise direction. The minus enantiomer will rotate light in the plane polarized light in the anti-clockwise direction. A racemate is a 50-50 mix, so it'll have no overall effect. So here's what I'm describing with the picture. We have a light source, we have unpolarized light vibrating in all directions. After it passes through a polarizing filter, it's only vibrating in one direction. Then we pass that plane polarized light through a substance containing, a tube or a container containing an optically active substance, and the effect on that is that it rotates the plane of the polarized light, and then we can observe how much it's been rotated by using an analyzer at the other end. Okay, the other thing is that chiral molecules react differently with other chiral molecules. It's like the idea that a right hand does not fit a left-handed glove. The molecule must be the correct shape for the molecule it's reacting with. So that's also a difference between enantiomers, is that some react differently with other chiral molecules because they fit. Okay, so as an example, most amino acids and therefore proteins are chiral, along with many other molecules. This is an interesting thing: is that many drugs are optically active, with only one enantiomer having the beneficial effect. In the case of some drugs, the other enantiomer can even be harmful. For example, thalidomide is an interesting case study. In the 1960s, it was given to pregnant women to reduce the effect of morning sickness, which led to many disabilities in babies and early deaths in many cases. The problem was that one of the enantiomers, the S enantiomer, worked as a sedative, but the R enantiomer had the effect of causing disability in babies or even death, unfortunately. So it was banned when this was found out. However, it's starting to be used again to treat leprosy and HIV, as long as the patients are not pregnant. Another example is S-carbone and R-carbone, two enantiomers of each other. One is found in caraway seed and the other is found in spearmint. Or S-limonene and R-limonene, one found in lemons and the other found in oranges. Okay, so that's an introduction to organic chemistry, naming, and different types of isomerism.